The general plan here to solve this system is to use a pair of these equations to eliminate one of the variables, and then use a different pair to eliminate that same variable. That process will result in us getting two new equations that each only have two variables, the same two variables. And so then we'll treat those two equations as a two-variable system and solve that. Then we'll back substitute to find that remaining third variable. So for convenience, I'm going to label these equations equation 1, equation 2, and equation 3. Now just looking at my different options here, the coefficients on the z's would make it relatively easy for me to pick a couple of different pairs and eliminate z. So I'm going to make a note that we are going to eliminate the z. So I want to pick just two of the equations, one pair, and eliminate the z. And the easiest pair to use would be equations 1 and 2. Now, I don't have to multiply either one of those by anything in order for the z's to be eliminated when we add them together. So I'm just going to take equations 1 and 2 directly and add them together. So I get 4x plus 6y, the z's are eliminated, equals 28. I'm going to call that equation 4. I'm going to have to use that later. Because it still has two variables, I need another equation to go along with it in order for me to solve for either of those variables. So I need to go back up to my original 3 and pick a different pair, meaning either 1 and 3 or 2 and 3, and eliminate the z again. I'll go ahead and use equations 1 and 3. And if I look at the coefficients on the z's, in equation 1 I have a negative 1. In equation 3 I have a positive 2. So for those to be opposite, I would need to multiply equation 1 by 2. That would make it have a negative 2 on the z to be the opposite of the 2z in equation 3. So keep in mind you have to multiply every term of equation 1 by 2. So we end up with 2x plus 8y minus 2z equals 40. And then equation 3 we don't need to change. We get 2x minus 3y plus 2z equals negative 16. Adding those two together, we get 4x plus 5y, the z's are eliminated, equals 24. So we're going to call that equation 5. So now equations 4 and 5 together make up a two-variable system. They both only have the variables x and y, and no z's. So we're going to stick those together here and treat this like a new problem, like it's a two-variable system type of problem. So we can solve that either by substitution or by the addition method. Since both have a 4x in them, if we just multiply one of them by negative 1, we will be able to eliminate the x's. So I'll go ahead and do negative 1 times equation 4. And then we'll keep equation 5 the same. So that'll give us a negative 4x minus 6y equals negative 28. And equation 5 will be 4x plus 5y equals 24. Adding those together now, the x's are eliminated. Negative 6y plus 5y is negative 1y. Negative 28 plus 24 is negative 4. Dividing by negative 1 on both sides gives us y equals 4. So we found our first part of the solution. Our complete solution will involve specifying values for x and z as well. So I need to go back to either equation 4 or 5, one of the two that only has an x and a y in it, and I'll be able to find the value for x because now I know that y is 4. So I'll go ahead and just use equation 5 right here, and I'll plug in a 4 for y. Now solving for x, we get x equals 1. Now we need to figure out the value of z. To do that, go back to any of the three original equations since they all involve z, and plug a 1 in for x and a 4 for y and solve it for z. I'll go ahead and use equation 2. I'm going to plug a 1 in for x and a 4 for y. Doing that and solving for z gives us z equals negative 3. So we write our solution as an ordered triple with the x-coordinate first, then the y-coordinate, then the z-coordinate. And we can check our answer by taking that and plugging it into each of the three original equations and making sure we get a true statement.